Greetings everyone, this is Mr. Mall. Today we're going to discuss strong versus weak acids and bases and some of the differences between these two types of compounds. So let's go ahead and get started. First off, we need to define what the difference between the two is. So when I say a strong acid or base, what I mean is when I throw this thing in the water, it completely or essentially completely dissociates into ions. And so it's very much like a soluble salt. We throw it in the water and all of it breaks apart into solution. So when I look at something like hydrochloric acid, I throw this thing in the water. My forward arrow is going to be huge. My reverse arrow is going to be so small we can hardly see it. Because basically there is no reverse reaction. All of my HCl is going to break apart into hydrogen ions and chloride ions as it floats in water. There's 7 acids that do this: hydrochloric, hydroiodic, hydrobromic, sulfuric, nitric, perchloric, and chloric acid will all dissociate essentially 100% when dissolved in water. You may also see this reaction written a little bit differently because as it turns out, when I have HCl, I'm going to leave out the phases for right now, and I dissolve it in water, H plus doesn't actually exist on its own. It always attaches to a water molecule in the form of what's called the hydronium ion. So you very well may see this equation written as follows, where the water has taken that H plus and then I have my little Cl minus floating around. So you may see either one of these. Bases, when thrown in the water, will do the same thing. They will essentially dissociate completely. And so I have the cation, and then I have the anion, which in this case is hydroxide. Now all the metals from group 1 are going to dissociate 100%, so sodium, potassium, that entire group is going to be considered strong bases, and there's a few other ones, but these are going to break apart completely into water. So I want to show you a strong base and prove to you what's happening at the molecular level. So I'm going to come back to this in a second. So here's our animation, and this is neutral water. Notice that about 1 in a million water molecules will actually self-ionize and break apart into water, and there I have those 2 water molecules coming together, and there's our H3O plus and OH minus. Now when I look at a strong acid, HA, you'll notice down here at the bottom that all of HA has completely dissociated. There is no HA in this whole solution. All of it has broken apart into A minus and H3O plus. And so when I'm looking around, you'll notice every single one broke apart. The pH is incredibly low. Now, if I have a strong acid, or I'll show you the strong base here too. Okay, here's my strong base. Here's my strong base, MOH. You'll notice that when I look around here, there's no more MOH. It is all turned into my cation and then my anion, hydroxide. It's completely broken apart. Now my pH is around 12. Strong bases, it doesn't really matter how much I put in here. I'll show it, I'll prove it to you. Let's go back to strong acid. So let's say I have a concentration of 0.01 molar. And so I still have a pH of 2, very low. Every single one's broken apart. If I were to have 10 times the concentration, so I actually pour in 10 times as much, let's see what that does. 0.1. Notice there's my change in pH. For every 10 times increase, the pH actually changed by 1. It is dealing with that whole log base 10, powers of 10. And so I have 10 times the concentration. I put 10 times as much acid in there. We can see there's 10 times as much acid. The pH actually changes by only 1. The same thing is with bases. And so there's 13. If I make it 10 times as much, our pH is going to change by 1. So essentially all of it broke apart. So let's go back to our presentation. A weak acid and base does not fully dissociate in water to form ions. And so what happens, this is very much like a slightly soluble or partially soluble salt. You throw it into water, but not all of it actually dissociates. Only a small percentage will actually break apart in water. So HCN is a good example. Notice my reversible reaction arrows. Very a small amount of HCN will actually break apart into hydrogen ions and cyanide ions. But most of it's going to stay in the form of HCN. So we call this a weak acid. Okay, this reaction lies very much to the left, whereas a strong acid or base lies very much to the right. So I want to show you what a weak acid or base looks like so that we can see the difference between the two. So I'm going to go back to the animation. So I'm going to go ahead and go back to, here's my strong acid. I'm going to change it to a weak acid now. And so as you look around here, the pH is not as low as it was when it was the strong acid. You can see that pH meter. And HA plus H2O gives me A minus and H3O plus in blue and red. You'll notice that there's still a majority of HA is still bonded, did not break apart at all, did not dissociate. And so weak acids or weak bases do not dissociate 100%. I'll show you the weak base as well. So I have my base plus water. Only a small percentage of those actually dissociated or broke apart into those hydroxide ions that they are in blue. You'll notice the pH was not nearly as high as it was just a moment ago. So this is the difference between strong and weak. Now when I say concentrated versus dilute, we're really talking about, remember, I'm going to change this to a weak acid. When I say concentrated or dilute, I'm really talking about how much acid is there. So if I change the concentration from 0.01 moles per liter to, let's say, 1 mole per liter, okay, we're going to have 20 times the concentration. You'll see, even if I pour a lot more in there, there's still not that much more acid because only a small percentage actually breaks apart. So the pH did go down a little bit, but it wasn't nearly as significant as the strong acid or the strong base. Alright, so let's talk about these weak acids and bases, and let's look at them mathematically. Okay. So what is an example of a weak acid? So the general form for a dissociation of a weak acid is I have my weak acid, HA. You'll notice I used HX the other day for a strong acid. So HA is going to break apart into water. A little reversible reaction here. Into H plus, my hydrogen ion, and then my anion, A minus. Okay, and you may also see it in the form we just said, HA plus H2O gives me H3O plus A minus. These are going to be comparable forms. You can see either one. So if I wanted to come up with because this is an equilibrium situation, there's also an equilibrium constant associated with this reaction at a set temperature. And so looking at my phases, just like we did with KC, I'm going to include only aqueous or gases, and they're all AQ. So I'm going to make my expression. Ka is equal to H plus times A minus, all divided by my concentration of HA. And so this is going to be for a weak acid. Because there's an equilibrium situation established, it doesn't all go 100% to the right. I'm going to have to use this expression in order to mathematically deal with these different quantities. Now all these Ka values will come from a chart or a chart value. They have them at certain temperatures. So what I'd like to do now is I'd like you to take out that worksheet, and we're going to do two examples from the homework so that you can see how this equation is going to be used. Alright, let's go ahead and take a look at the homework. So this is going to be worksheet 6. Get this now. So I'm going to do number 1 together with you. At the top of this worksheet, I'm going to leave some spot for the second part, but I would put my Ka is equal to what I just wrote for you. H plus times A minus, all divided by my concentration of HA. Now this is for weak acids and weak bases only, because remember, you don't need to know this whole equilibrium situation if you're dealing with a strong acid. They 100% break apart. So HA is a weak acid. Determine the Ka value if 0.5 moles per liter of HA solution has a pH of 4.0. The other thing I'd like you to write at the top of this is that if we're going from pH to the concentration, we're going to use that power of 10 rule. 10 raised to the negative pH will turn me into the concentration. So there's a couple things I need to do. First off, we're going to write the equation. HA is a weak acid, so I'm going to draw a dissociation equation for this acid breaking apart. So throw this thing into water. Don't know how much it breaks apart, but it's a weak acid, so probably not a whole lot. Breaks apart into H plus and A minus. Okay, those are both aqueous. So when I have this, I'm going to put my concentration here, 0.50 moles per liter. That's going to be my concentration that I put into my solution. However, not all 0.5 moles per liter is going to dissociate. Remember, only a small percentage of weak acids will, so I can't therefore say that H plus is 0.5 and A minus is 0.5, like we would do with a strong acid, which completely breaks apart 1 to 1. So what we have to do is we have to take our pH, and we need to figure out how much, what is our concentration of H, because pH is just a way to tell me the concentration of H. So I'm going to take 10 raised to the negative 4. It's going to give me my H plus concentration, which is just 1 times 10 to the negative 4th moles per liter. 10 raised to the negative 4. Simple enough. So this is my concentration of H, pH, in solution is going to be 1.0 times 10 to the negative 4th moles per liter. Now when I think about water, neutral water is 1 times 10 to the negative 7th, so this is clearly more than water. So I'm going to go ahead and my pH meter tells me I have 1 times 10 to the 4th, so I'm going to put 1 times 10 to the negative 4th moles per liter. Now if I have one of these, then I'm going to have one of these as well, to 1 to 1 moles per liter. And so this actually tells me now how much is actually dissolved. And so the last step to find Ka, we're going to make our Ka expression is equal to, in this case, H plus times my A minus, all divided by the concentration of HA. And so now it's just a matter of plugging these values in. My H plus was 1 times 10 to the... Now let's talk sig figs. Right here on my pH, these last two zeros are going to be significant. So what I would actually need to do here is I would say that this is 1 point. I need 2 sig figs. So I'm going to go ahead and rewrite this for you just to be consistent as 1.0 times 10. 1.0 times 10 to the negative 4th. Sorry about that. Okay, 1.0 times 10 to the negative 4th. Now I'm going to multiply that basically squared, 1.0 times 10 to the negative 4th. And then that's all divided by HA, which was 0.50. So I punch these values in my calculator, and I'm going to get a final value that K is equal to 2.0 times 10 to the negative 8th. Okay, you don't need a unit on an equilibrium constant. So this is how we can solve for this. We're going to need to use our pH in order to figure out how much actually of this acid dissolved. Alright, let's go ahead and take a look at question number 4 as another example. So here I'm actually dealing with a specific type of acid, acetic acid. I'll give you the formula for this one. Acetic acid is basically acetate with an H on it. So acetic acid is CH3COOH. This is a structural formula. Whenever you see the COOH, that H is usually signifying that this is some type of acid. So this is acetic acid. And so I'm going to draw my reaction for this taking place, CH3COOH. Okay, and that's going to be dissolved in water. And this is going to be a weak acid breaking apart. And so what do I need to do with this thing? I just need to remove an H, because all acids are H plus donors. So CH3COO minus plus H plus. And so these are ions in solution. Now it tells me that I have 0.35 moles per liter of acetic acid solution. That's my concentration of acetic acid. But not all of these molecules are going to break apart into ions in solution. So we need to figure out how much there are. Now they actually give us the Ka in the problem. And so I don't have to solve for Ka. So what we need to do is we're trying to figure out how much acid actually dissolved. And if this is 1, this is going to be 1, because this is just a 1-to-1. And so we're going to use a little algebra now. Using our Ka expression, Ka is just equal to, in this case, CH3COO minus concentration times H plus, my products, over my reactants, CH3COOH. And now I can plug in. Now x times x. And so really I have x squared on top, divided by, on the bottom I'm going to have 0.35. And because I know the value of Ka, I can set this up equal to 1.8 times 10 to the negative fifth. Okay, and you can just think of that number as being over 1. Do a little cross multiply. X squared is equal to 6.3 times 10 to the negative sixth. And so when I solve for x, take the square root of both sides, x is going to be equal to 0.0025 moles per liter. So a very small percentage of these actually dissolved or broke apart. Okay, so let's do this last step. We just solved for what x was, which turned out to be my H plus concentration. Let's go ahead and put that in there. 0.0025 moles per liter. Now the next question, now we're going to use some of those pH equations to go back and forth. That little table would be helpful. So let's do the first one. To go from H plus to pH. Okay, what am I going to need to do there? So to ever define pH, we're just going to take the negative log of our H plus concentration. So I'm going to punch that on my calculator, and we'll get the pH as being, I'm going to use, here's my 2 sig figs, so 2.1 sig fig, 2 sig fig, 2.60. To go to OH, there's a couple of different ways I could do this. I could take my pH and find the pOH, which is just 14 minus 2.60, and then I could go back this way. I'm going to do it a little bit differently. I'm going to take my H plus and go to OH by using the Kw for water. Kw is equal to concentration of H plus times concentration of OH minus. And so what I can do then is I can, because I know one of these, I can solve for the other. And so when I rearrange this equation, I'm going to erase that and do it a little different way. When I rearrange this equation to solve for OH minus, we're going to get that's equal to 1.0 times 10 to the negative 14th, which is just Kw, divided by my H plus, which is 0.0025. And when I divide those out, I'm going to get this is equal to 4.0 times 10 to the negative 12th. There's more than one way just to get there. Like I said, you could go from pH to pOH and then take the negative log of my pOH, or you could take 10 raised to the negative pOH. There's a couple different ways you could get to this, but at the very end you should be getting that answer there. Before I leave this worksheet, I just want to give you a quick hint on number 3. Remember, if something is a percentage, that always means, percentage always means out of 100. And so when I'm talking about 5.5 out of 100, you can use that as a conversion factor. So for example, if I have 0.03 moles per liter, and it's only 5.5% ionized, well, that means that if I had 100 moles or 100 moles per liter, that 5.5 out of 100 would actually dissolve, and that's going to help you find your concentration. So there's a little hint for that one. All right, so let's wrap up our discussion on weak acids. So there's our weak acid. I do want to show you a weak base. They're going to be kind of similar. So here's the reaction for a weak base. I have my base plus water, and it's going to slightly break apart into water. And my water is going to get its H removed by the base, leaving OH minus. And then the base is going to pick up that H plus, and it's going to gain a charge positive, whatever that was. And so whatever my base was, it's going to have an H and then a plus added to it. And so if I look at my Kb expression, we can say that the Kb is equal to the concentration of B H plus times the concentration of OH minus, all divided by concentration of, this is a liquid, so we're not going to worry about that, our concentration of our base. All of these other things are going to be AQ. And so this is a KB. It's very similar to Ka, so I just want to really quickly do an example for you of a reaction. So here's a reaction. This is ammonia, NH3. And ammonia is not ammonium, which is actually on the right-hand side here. So ammonia is a very weak base. It will actually remove H pluses from water to form hydroxide ions. And so here's my reaction. I'm going to draw my equilibrium arrow here. And so this is a weak base, so I'm going to go ahead and figure out what my Kb is. And I'm going to go ahead and give you a value, and I'm going to say, let's pretend that I dissolve 0.030. Now, because this is a weak base, this is not going to dissolve very much. Yes, this number would go down a little bit, which would throw off your equilibrium, your Kb calculation. However, because it dissolves so little, we're going to say that this number is we're going to assume it's fairly constant. Okay, so assume constant. So this is going to break apart. And I'm going to just give you some numbers here. Let's say when I dissolve this in water, you could solve for this, or you could be given it in the problem. Let's say I have 0.001 actually dissolves. And so to find Kb, we would take our Kb expression here. Kb is equal to concentration of NH4 plus. Now notice NH3 plus a hydrogen ion becomes NH4 with that positive charge. All divided by NH3. And so I can just plug in my values. 0.001 times 0.001, all divided by 0.030. And so I punch that in my calculator, and I'm going to get a Kb value of 3.3 times 10 to the negative 5th. Alright, well this has been a video explaining the difference between weak acids and weak bases. I want to leave you with one last little thing to kind of show you another application of this, and that's going back to the animation here. One thing that's really cool about the weak acid and weak bases is because they're ions in solution, they're going to conduct electricity. So when I have my little conductivity meter, okay, you see these lights here. Let's go to water. Water has a very, very small amount of ions in solution. Remember, we said that about 1 in a million water molecules will break apart into ions. So that's why water, when given a strong enough current, will conduct a current, because there are ions in there. It's just the concentration is so small. So when I go to a weak acid, okay, it gets brighter because there's more ions. Go to a strong acid, super bright. Same thing with weak base. Okay, a decent amount of ions in there, strong base, strong amount of ions. And so I can leave that conductivity sensor in here as well. Let's talk about if I have concentration change. Let's say it was all a weak acid. If I have a lot in there, 1 mole per liter, it lights up more. There's more dissolved. If I reduce the concentration, let's say by 10, it's not quite as bright. Say I reduce it again by another power of 10. Okay, it gets a little bit softer, and then so on and so forth, and it gets a little bit weaker. So the more ions that are in there, not only is it more acidic or basic, but you can actually see the conductivity change based upon those. Alright, well this has been a lot, and what I'm going to do is that you're going to be able to work through this worksheet now, and I hope that this has been helpful. Feel free to come back and watch this video at any time.